Okay, maybe before we start, I will start the opening first. Assalamualaikum warahmatullahi wabarakatuh. Salam, Om Swastiastu, Namo Buddhaya, dan salam kebajikan untuk kita semua. Good afternoon, ladies and gentlemen. Welcome to another session of SEMAT, or Seminar Jumat, or the Friday seminar. Well, it's usually held on Fridays. Today we have a special exception because we're gonna have it on Thursday. But don't worry, because we're about to delve into and discuss fascinating geology topics, of course. But before that, let me introduce myself. My name is Tara, an undergraduate geological engineering student at Institut Teknologi Bandung, who will be your host for today. On today's seminar, we're going to talk about an interesting geology topics on title, Modeling Magma Overpressure and its implication for eruption triggering and style. But first of all, I would like to greet and welcome our honorable guest speaker, Mr. Mike Cassidy, Associate Professor at Birmingham University. Good afternoon, sir. Thank you for joining us, and we are really excited to welcome you on today's seminar. Thank you.
Thank you, Tara. Thank you very much.
Thank you. I would also like to greet Mr. Idam Andri Kurniawan, Mas Idam, and also Mas Mirzam, lecturer of geological engineering student who helped us to hold this event. Selamat sore, Mas Idam. Okay, maybe we can start for the opening.
Thank you, Tara. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon and good morning in London, in Birmingham, sorry. And then today, on behalf of the head of the graduate student, Pak Mirjam especially, I would like to say thank you very much to Mike that you always give the lecture in our program. I think today also we have the good tema about the modeling magma overpressure and its application for eruption triggering and style. So I think the student will be you have good experience or you have good knowledge about these activities. I mean, so hopefully you can enjoy the the lecture. Okay, that's all for me. Thank you very much.
Thank you, Mas Idam, for the opening speech. Ladies and gentlemen, we are now going to move to our main presentation, who will be presented by our guest speaker, Mr. Mike Cassidy. For Mr. Mike Cassidy, time and screen is yours. Thank you.
Great, thank you, Tara. Thank you, Idam and Mirzam. It's great to be back, and salam alaikum, and it's great to be able to speak to you today again. I think so. Last time when I've given talks to ITB, I've given talks about eruptive style and eruptive deposits, and previously I've given talks about large magnitude eruptions and the hazards and risks that they pose. But today I want to do something slightly different, and I want to talk about modeling. So some of the work that my PhD student, Anna Brookfield, has done during her PhD whilst in Oxford. I used to be in Oxford University. I'm now at the University of Birmingham. And so it's a collaboration with Anna, my PhD student, and some other people that I've just noted down there as well. So it's really a combination of different people. So I want to talk about magma overpressure. And this is something that's not necessarily talked about so much in volcanology, but I think it's really important actually for governing lots of different processes. So what is magma overpressure? We say it's the pressure in excess of lithostatic pressure. In other words, if you have a magma reservoir at 2 or maybe say 4 kilometers underneath the surface of the crust, then that, because of the weight of the crust, will have a lithostatic pressure. But because of processes that I'll talk about today, you also might have excess pressure in the reservoir, in the chamber, and that's what we call magma overpressure. So it's been important to look at this because it's often being suggested that this is the trigger for volcanic eruptions, particularly volcanic eruptions that go from the bottom up. So sometimes implicated in eruptive style as well. There's a paper in the 90s that talked about that as well. So we're going to investigate that in a bit more detail today. Now, with generating this overpressure, there are several different ways you can do this. Some of those things are external to the magma, so it could be that you're looking at earthquakes, or the crust is actually squeezing in tectonic forces. But actually, I'm going to talk about the ways that you can generate magma overpressure internally from the magma itself. So this might involve magma injection, so injection of magma from maybe a deeper reservoir into a shallow magma reservoir. That increases the volume of the magma reservoir. And that might not just be magma, it could also be fluid that comes into the system. So fluid comes into the system and it creates more space, or for the same amount of space, it kind of produces more pressure. For larger magnitudes or larger magma bodies, buoyancy is thought to be quite an important mechanism for generating overpressure. So buoyancy, causing things to float up if it's less dense than the surrounding crust. So if there's lots of bubbles inside the magma, or even water-rich lenses, then this will cause the magma to ascend just like a balloon might. But that magma will be trapped by the walls of the reservoir around it, by the crust keeping it in. And that can actually generate overpressure, that process of buoyancy. But I'm not going to really concentrate on those two today. I'm going to concentrate on this third one, which is how we can generate overpressure through volatile exsolution. It's a process sometimes called second boiling. So what this is essentially you cool down a magma. So this is a very normal thing to do. As a magma injection comes in, it will start cooling down. And as it starts to cool down, the magma will start to crystallize. It will start to form crystals like olivine or pyroxene or plagioclase. Now, these minerals are very water poor. So when you crystallize some of these minerals, it makes the surrounding magma more water rich and more volatile rich. So not just water, but other volatiles like sulfur and carbon dioxide and things like that. So when you generate more bubbles and more volatiles by cooling down a magma reservoir, you generate this overpressure. So this is what I'm going to talk about today. And I think this is interesting because I think we can link this potentially with monitoring data, potentially unrest signatures, and also timing. So I'm just going to talk about a volcano that some of you might know. This is Kelut in Indonesia. It's the other side of you guys in Java, East Java. And it's had lots of different, it's a very active volcano with lots of different types of volcanic eruptions. So in 2007, you had this effusive eruption of a magma lava dome growing inside a crater. But in 2014, it was a much more explosive eruption. But luckily, PV and BG, they evacuated people and very few were hurt. So let's look at the triggers to the 2007 effusive volcanic eruption. So the triggers of this eruption included a long period of seismicity, earthquakes in the upper crust and in the mid crust as well. So quite deep underneath the system. We also had, this is a picture before the volcanic eruption, where you collected this lake water. I think now there is still, it's collected a lake since the 2014 eruption. So before the 2007 eruption, there was this lake, and we saw that the lake was increasing in temperature, which was interesting. And then some of the experiments that I've done in my lab, we worked out that using petrological methods, that the 2007 magmas were stored at higher temperatures, and they had what we call mixed volatile saturation. And what I mean by that is that we had not just water as a volatile component, but also lots of CO2, which was interesting. And then another piece of the clue, or piece of evidence, I guess, in this mystery, was that before the eruption, Corentin Cadron, which I know some of you will know, he showed that there was lots of CO2 degassing into the crater lake. So lots of CO2 going into the lake as well, months before the eruption. So what does this tell us about what could have triggered the volcanic eruption, this effusive eruption 2007? Well, we have lots of CO2, we've got higher temperatures, increased temperatures months before, and lots of deep and mid and upper crustal seismicity. So this tells us that we think it's triggered by deep magma recharge into the system. Probably something that was quite rich in CO2. 2014, the triggers that led to this explosive eruption were quite different, actually. So we had less than 4 weeks of shallow seismicity, and actually it only really ramped up in the last 11 or 12 days before the explosive eruption. We had a study showing, looking at satellite INSAR, essentially telling you how the magma, how the edifice can expand or deflate, measured by satellites. Everything all right there? Good. And then this showed us that there was no deformation, no deep deformation 3 months prior to this explosive eruption. Okay, so there doesn't seem to be magma coming into the system. And then I also did a study in geology that showed, looking at these crystal textures. This is a plagioclase crystal, and it showed lots of different compositions of both higher northite and lower northite, different compositions of plagioclase. And also we measured the melt inclusions within those particular zones as it grew from the inside to the outside, much like a tree would grow. So right at the rim, so in other words, the youngest part of that crystal is what the magma experienced. And what we saw is that the magma experienced a cooling and also that it increased in its water content. So this is really interesting because it was going through these cycles, as I show here, of being hot and water poor and being cold and water rich. So Kelut seems to go through these cycles up and down through its history. And we think this is modified by magma injections that come in, they dilute the water content in the magma reservoir. And then as the magma starts to cool, it starts to increase in its volatile content. And this is what we saw right before the 2014 explosive eruption. So all of these components together, both from the monitoring, from the petrology, from the seismicity, all seem to suggest that this eruption wasn't triggered by a magma injection or an earthquake or anything like that, but seemed to be triggered internally by volatile overpressure, simply by cooling down the magma reservoir. One of the things we wanted to do, so this is a really interesting thing. The magma was triggered by itself, essentially, by cooling down the magma reservoir, causing that overpressure. One of the things we wanted to do was to understand whether unrest times, so the time of where the monitoring data, for example, seismicity, deformation, or gas data, for example, was correlated with the eruption triggering, so how the eruption might be triggered. So in other words, are unrest times linked to eruption triggering? Because what we've seen here, what we've shown with Kelut, is that the explosive eruption had a very much shorter run-up time, shorter unrest time compared to the effusive eruption. So we did a compilation of all the volcanic eruptions of a significant magnitude, and we were calling that VEI 4, so volcanic explosivity magnitude index of 4. So since 1992, that's because we were looking at the satellite era, which started around 1992. And about over half of these, 52% of these, showed only a month of unrest, and most of those had very little unrest. So here's a compilation of some of those volcanoes. You can see here, different volcanoes in different years. They were all pretty explosive. And on the, so that's on the y-axis there. On the x-axis here, you can see the days of unrest. And here's a broken scale where this is the time in a month, and then this is a time in a year, and then this is the time over a decade. So some volcanic eruptions show, so for example, this is Kelut in 2014. You can see that some deeper distal seismicity was seen about 28 days before the eruption over here. Most of the normal seismicity was only recorded 10 days before, and then we had some deformation just right before the eruption. But there's lots of other volcanoes that show a similar amount of short unrest periods. And this is why we entitled that paper Explosive Eruptions with Little Warning. With other volcanoes, so for example, Okmok, which is over here, this 2008 Okmok eruption, and Grimsvotn, which is in Iceland, Wolf as well. These all had periods where you had long periods of deformation, so there was long periods of swelling of the edifice, but actually the seismicity that was recorded was only really quick before the eruption, so short seismic run-up times. And obviously this is concerning because a lot of the ways we forecast and predict volcanic eruptions in Indonesia and the US, across the world, is principally by looking at seismicity. And what this tells us is that seismicity can only sometimes give us a very short warning before volcanic eruptions. And also we found that magma can sometimes, like Kelut, reside in the crust for long periods undetected, and then can be triggered internally by this process of volatile overpressure, and very quickly. So Kelut is an example, Calbuco in Chile in 2011 is another example as well. So we wanted to explore and model, and this is what this talk is about, if volatileic solution, this idea of cooling down the magma reservoir, increasing your volatiles in the residual magma and causing bubbles to form, causing that overpressure, is that a viable trigger? And so does that trigger work in other words? And what's its role in controlling the explosivity of a volcanic eruption? So let's talk about what causes explosivity. Okay, so this is a paper of mine in 2018 where we compiled the ascent rate of all the volcanic eruptions that we had ascent rate constraints for, measured in different ways, so measured by monitoring or by petrology or experiments, or bubble number densities and microlite number densities, the type of stuff that I know IDAM does as well. And how does this relate to eruptive style? So what we found, so we're looking at this graph here now, and on the x-axis this time are different volcanoes and different eruptions, and on the y-axis here is their ascent rate. And what we find generally is that the effusive eruptions, those that are in red, are found at slower ascent rates relative to the eruptions in black, which are generally found at higher ascent rates. So there is a messy line, dividing line, between some of these effusive and explosive eruptions. And this is exactly where we see those fast transitions between effusive and explosive eruptions. So at ascent rates of, for example, 0.01 meters per second to 0.1 meters per second, these are the types of volcanoes. You might be familiar with them in Singabang, in in what's the other one I'm thinking about? I'll come back to that. Ceramu as well, for example. These are the types of ascent rates where you see sometimes the eruption shows it produces a lava flow or a dome, but very quickly afterwards it produces an explosive eruption. And we think that it's because they're at these intermediate ascent rates that are able to go into explosive or effusive quite rapidly and change between those. So what we know from this graph and from this compilation and from the literature is that ascent rate, but also outgassing control, essentially how easily the magmas can release their gas, these are very much linked. And we know that these control whether you have an explosive eruption or an effusive eruption. But what we don't know is whether it's related to the initial ascent rate. For example, is it driven by the overpressure from beneath, or even decompression, so the going from top down? Does that affect how easily the magmas are outgassed and therefore affecting the explosivity? So remember that the gases inside volcanic eruptions, they really power explosive eruptions. So we need them to stay with the magma in order to produce an explosive eruption. So what I'm asking here is it driven by the initial ascent rate, or is it that you have outgassing prior to ascent that actually slows how fast the magma comes up? So if you have outgassing before, then you have less volatiles in your magma to give you the buoyancy to drive you to drive fast ascent rate. So what we don't know is kind of which way round it is. Is it fast initial ascent rate that all the gases stay in, or the gases leave and then you have slow magma ascent? So this is one of the things that we wanted to find out. Okay, so let's try and model our overpressure. So to simulate this, we use the MELTS thermodynamic model. This is something that you all can use as well. It's a fairly easy model to run, and you can use Excel with it and things like that. And what you can do with that is you can simulate a magma cooling down, magma crystallizing, and as the magma crystallizes, it drives exsolution of volatiles like water, like CO2 into the magma. So we define overpressure here as the change of volume, delta V, divided by the volume times by the beta, which we're calling compressibility. Okay, so the changes in volume and compressibility relate to crystallization, the loss of melt, and the exsolution of fluid per 1 gram of magma. And when we're talking about volume change, this component of the equation here, we assume that we have a rigid surrounding crust. So the volume changes due to cooling result in pressurization instead of the magma accommodating or the crust accommodating the magma and the reservoir expanding. We're assuming that the crust stays rigid, and I'll talk about that later. And of course, this will vary. This equation will vary depending on the composition of the magma, whether it's a basalt or an andesite, for example, the temperature of the magma, how much volatiles you put in to start with, and also the type of volatiles, whether it's water, dominated by water, or perhaps there's CO2 in there as well, carbon dioxide. Okay, so let's visualize these two equations, these two components in this equation on a graph. So what we're going to do here in this scenario is cool the magma at 60 megapascals. So that's assuming that the magma is sitting in the crust about 2 or 3 kilometers within the crust. This is where we think the Kellut magma reservoir was stored. And we're assuming that it's initially lower in volatiles, and we're calling this undersaturated. So the volatiles are not saturated in response to the magma itself. Okay, so they're undersaturated and they start cooling the magma at this shallow depth. So what we have and this is what we're looking at here. Let me just see if I can get my laser pointer thing. Yeah, that's a bit better, isn't it? So here we have on the y-axis here, volume change. And on the x-axis, we have cooling temperatures. So we start off the magma at about 1,100 degrees, and the magma starts crystallizing over here. And as it starts crystallizing, the volume actually decreases because we're compressing the magma slightly. But then, as it starts to, as it starts to form these fluids that come out of solution, they exsolve, they're in X solution now, then the volume changes quite rapidly and increases, okay? So it increases as the magma starts to cool, okay? But actually what we see is that the peak overpressure is not at the highest volume change, and I'll explain why in this next graph. So this next graph is explaining compressibility, so this beta factor that we talked about here. And this basically tells us how squishy our magma can be, if you can compress it or not. So if you have a magma that has no volatiles in, no bubbles, then essentially it's incompressible. It's got a compressibility value of 0. As you start to form bubbles, exsolution, like water, for example, you start to increase your compressibility. But at this stage, as it gets to about 900 or 950 degrees, the compressibility is too high. And what happens is that the overpressure can be accommodated by essentially, it can be dampened by this compressibility. So actually what you need is, in order to generate the highest overpressures, so remember, if the beta part of the equation is too high, then you're going to reduce your overpressure. So it's a balance between volatile expansion and compressibility, and that's why the peak overpressure is found sort of in the middle between not too compressible, but also enough of a volatile expansion by fluid release. So when we put these two equations together, volume change and compressibility, so basically this, which is that, change of volume, and then compressibility, which is this, then we get overpressure. So now we have on this axis overpressure in megapascals, going from 0 up to something like 30 or 40 megapascals, which is quite high. But you can also see that there's some underpressure as well. Okay, so now we start off with a volume change. Our volume is decreasing, and we're reducing the volume of the magma reservoir as we start cooling. And this is because we have crystallization. So this actually is the pressure's reducing and the compressibility is 0. So this means we have a really sharp underpressure at the very start. But as soon as we get to the point of fluid exsolution, then this rapidly increases. And we get a really large increase in overpressure as the volume changes, as fluid comes into the magma reservoir. And it peaks about this point over here, about 1,000 degrees temperature. If it cools down further, then there's too many volatiles and the magma just becomes too compressible in order to form these high overpressures. What was really interesting, this is done with a Kelute, assuming Kelute magma composition, assuming the right pressures and temperatures and things like that. What we find is that the peak overpressure, we think, is found at 1,000 degrees centigrade. Now this is the same eruptive temperature of the 2014 explosive eruption that we measured from experiments. So it's telling us something quite interesting, that actually there is this sort of temperature in these conditions that is forming this volcanic eruption. Right. Hope that makes sense so far. So we now have our overpressure equation that we've just seen. And I should say that this is this study that I'm talking about today has been published in a paper called Brookfield et al. 2023. That's in the journal Volcano and Geothermal Research. So you can have a look at that afterwards. One of the things we wanted to look at is not just how the overpressure evolves as magma cools and crystallizes, but also how volatiles might impact this overpressure. So now what we're going to do is vary the initial water content of the magma. So this is this graph over here. So the graph I showed you in the last slide was an undersaturated magma. In other words, we didn't put enough volatiles in for the magma to start to be saturated in volatiles. So it had to cool down quite a bit in order to get to the stage where it could start to have enough volatiles in the residual magma to start to exsolve from the magma. But if they're already at the point of saturation, so the volatiles are not bubbles yet, but there's saturated in bubbles, then we can call this a saturated magma. Interestingly, if we start off with a magma with really high volatiles, high water content, then actually we call it oversaturated, and this is where there's already bubbles within the magma. So this was really interesting when we did this, because what it shows is that there's different things. If we start off with too little water, we find that the volume expansion that we get in to form that overpressure is too low generally, okay, to form really high overpressures. When we put lots of water into the system, into the magma system, actually we find that the compressibility is too high. So in other words, any sort of overpressure is dampened by the amount of volatiles and bubbles in there. But when we put in just the right amount of volatiles, a saturated amount, then we found that this had the highest change in overpressure and highest peaks in overpressure compared to the low water content and compared to the high water content. So it shows us that there's this sweet spot in the middle where a magma with just enough water seems to produce the highest amounts of overpressure. So remember that for later. So this is not looking at Kelut this time. This is looking at Nisseros in Greece, a Greek island. It's using a different pressure, using a different composition. But if we were to use other magmatic systems with different compositions and different starting volatiles, we find the same pattern, okay? So this is Nisseros, I just showed. This is Calbuco in Chile. Kelut, we're aware of. Mount St. Helens in the US. And we're starting at different pressures. These are different magma compositions, but we see the same pattern in water contents. So the highest overpressures are always found where the volatiles are saturated in respect to the magma. When there's too much water or when there's too little water, you just don't reach the same heights, the same magnitude of overpressures. And we see this for the thicker blue lines in all of the scenarios which are at the saturated conditions. So that's really interesting. So there does seem to be this sweet spot in magma volatile contents that determines your overpressure. Now, what if we don't vary water, but actually we vary another volatile component? So let's instead now understand the second biggest volatile in volcanic eruptions generally, and volcanoes, is CO2, okay? So a little bit of CO2 into the magma is common, and sometimes for some volcanic eruption there's a lot, and sometimes there's actually none at all, okay? So let's see what happens to the magma and to the overpressure when we add different amounts of CO2. I'm going to use this notation called XH2O. This essentially is the fraction of water compared to CO2. So when you have an XH2O of 1, that means it's pure water, there's no CO2. And as this value gets lower, then the fraction of water gets lower, there's more CO2. So 0.9 means that there's actually some CO2, more CO2 than in this mixture than the pure water phase. Okay, so interestingly, we find that if we add the CO2, our overpressures come down, they all reduce. And you can see this from the pure water phase that we're seeing in different compositions from Calbuco to Kelut to Mount St. Helens. Anytime that you add CO2 into the mixture, it reduces the overpressure. Now, the reason it does this is because you have a huge amount of compressibility or produced by CO2. So CO2 is a gas that likes to come out of solution much deeper in the crust than lots of different volatiles like water. What that means is it forms bubbles very low down. Once it gets to these sorts of pressures that we're looking at, relevant for magma reservoirs around 4 or 5 kilometers, 160 megapascals, 230 megapascals. When you get to that stage, most of the CO2 is already formed as bubbles. Okay, it's come out of solution. It's come out of solution. And what this means is that it adds to the compressibility in a huge amount. And as it adds to the compressibility, it reduces the overpressure. So what we're finding is that optimum, there's a sweet spot of water contents, not too high, not too low, just right in the middle. There's also a sweet spot of the type of volatiles, in that we're seeing CO2-rich magmas do not produce high compressibilities, high overpressures. So I've just showed this for a model that we were just showing for 1 gram of magma. But what we've also done is combine this with a thermal model. This is from Gregor Weber in 2020, and it solves for heat conduction equation. Okay, so now what if we cool down the magma reservoir? And here we're assuming that all the magma reservoir cools as 1. Which we know doesn't happen, okay? We know that when we have a magma reservoir, it's the edges of the magma reservoir that are next to the cold crust that start to cool down faster than the interior of the magma that stays hotter for longer. So now what we've done is we've put in magma overpressure values for each pixel of this particular thermal model. So this particular temperature evolution might just give us 1 pixel evolution, for example. And here we're assuming that it's a closed system reservoir, there's no magma volatile injections or loss. We're assuming that it's cooling by conduction, not by convection. If it was cooled by convection, everything will be way faster, and I'll talk about that in a second. And we're assuming that the overpressure values that we're going to get are averaged across the whole reservoir. The other assumption we make is that once you get to 60% crystallinity, so the magma cools to 60%, we're assuming that the magma is no longer eruptible. And this seems to be fairly consistent across the board, that we see that the magma at this stage of its crystallization history just becomes too locked up. It can't flow, the viscosity becomes too large generally. Okay, and then what we've decided to bring in is a threshold for your critical overpressure. So in other words, what particular, in order to cause a volcanic eruption, what value of overpressure does it need to overcome? So this is dependent on the rock strength, tensile rock strength of the crust around it. This varies with how fractured the crust is, how altered it is, how much pore fluid there is inside the crust around magma reservoirs. Generally, what we find is that the tensile strength of rocks is about 5 to 10 megapascals, and the shear strength, so in this dimension, so tensile, remember, is pulling the crust apart. Shear strength is causing a strike-slip movement. Shear strength is generally twice as powerful, twice as strong as the tensile strength. And what we're assuming here is that in order to cause failure of the rock, and by failure I mean a rupture in the magma reservoir to cause an eruption, and to cause the magma to ascend upwards, we're assuming that it's 2 times the tensile strength of the rock. So we're using thresholds of something like 10 to 20 megapascals in order to cause an eruption. But you know, actually, that the rocks around magma reservoirs don't behave in a purely elastic way often. Often they will have a thermo-viscoelastic response of the crust, and that can accommodate some of the overpressure that we're talking about. So to allow for this, we're increasing the threshold by about 20%, suggesting that a critical overpressure that we need to cause in order to cause a volcanic eruption is about 24 megapascals. So it needs to get above this overpressure to cause a volcanic eruption. And we're not assuming where the actual breakout of the rupture and the tensile structure will be. Okay, so now let's look at how the overpressure varies throughout the magma reservoir in our thermal model. So what we have here is our temperature of a magma reservoir. You can see at 1,000 years after we start the simulation, you can see that it's cooling right at the edges of the magma reservoir, but actually the middle has stayed the same. And then as you go down here, this is 4,500 years, you can see that it's cooled much more. And then we apply our overpressure calculation to each of these pixels within here, and it gives us an idea, a picture of what the overpressure is also doing. So here you can see the reds are high overpressures, and you can see that the overpressures at 1,000 years are all related to the edges of the magma reservoir. And as it goes from 3,000 years to 5,000 years, the overpressure is more concentrated in the middle of the magma reservoir. So this is what it looks like when we scale up and we average every single pixel together. Essentially, it does something very similar to what we described in our thermodynamic model. So over this particular axis, we have the average reservoir overpressure, and on that's the y-axis there. And on the x-axis this time, we have the time. So this is time in thousands of years, 1,000 years, 2,000 years, 3,000 years, 4,000 years of it cooling down, okay? So if we have a magma that has loads of volatiles within the magma, it's oversaturated, then actually it takes quite a lot of time to reach the peak overpressure, okay? So these red lines here, I've denoted over here, these are denoting where we exceed the critical overpressure in order to cause a volcanic eruption, okay? So in our saturated magma case, we can cause an eruption very quickly. We can overpass this initial threshold very quickly. For oversaturated magmas, lots of volatiles, it actually takes a long time, maybe 1,000 years. In undersaturated magmas, it can take even longer to pass through this threshold. Okay. These timescales, as I said, are probably overestimates because we're looking just at conduction cooling rather than convection cooling, which will be orders of magnitude faster. And if we add CO2, we see the same picture, actually. that if you have a pure water magma, it's very easy to overcome the 24 megapascal overpressure. When you start adding little bits of CO2, actually it takes longer to cross this threshold. And if you've got lots of CO2, like down here, it actually becomes even very tricky to pass this overpressure threshold completely. So actually, these types of magmas where we have lots of CO2 in, it's really hard, we think, to trigger a volcanic eruption with volatile overpressure. So in other words, cooling down a magma with lots of CO2 will not form an eruption through internal means. It has to be triggered by another mechanism. In other words, this is probably why we have the effusive eruption, which was triggered by magma injection into the system, rather than in the explosive Kalut volcanic eruption, which had a pure water phase. This was triggered by, we think, cooling of the magma reservoir. So here I've assumed that we have a magma overpressure and the pressurization is all averaged across the whole reservoir. And this is an assumption, and I think it's probably not strictly correct. Sometimes we have areas within the magma reservoir. Perhaps there are areas around crystal mushes. We have lots of crystals where the volatiles could become trapped. And this is where potentially you get localized areas of overpressure. It's also potentially that you get lots of overpressure in the middle, on the outside of a magma reservoir, and we're assuming that they're all averaged, but that might not be the case. The overpressure might not be equaling out on a fast time scale because of viscosity. So there could be pockets of higher overpressure and localization as well. And this could cause localized eruption of the magma reservoir. And I think this is probably the case because when we look at already crystallized magma bodies that are next to crust, and this is an example from Torres del Paine in Chile, we find that at the edges of a magma reservoir, there's lots of outshoots and intrusions from the magma reservoir into the surrounding host rocks. So there's almost certainly pockets of overpressure that are rupturing. Okay, so it's not all this average sense. I also mentioned earlier in the talk about the fact that magma stress can be accommodated potentially by the surrounding crust. So to look at this, we've also used the idea of timescales to help us. What we're assuming here, so to trigger an eruption, we assume that the overpressure has to build up quicker than it can be dissipated by relaxation of the crust. So in other words, the magma will start to very, very slowly accommodate the stress within the crust. This will be a process controlled by the host rock viscosity, and it's also defined by the critical overpressure as well. So to do this, we worked out this calculation. We've defined this line, which occurs, the relaxation occurs within about 1,500 years. And when we match up our saturated magmas, our oversaturated magmas, our undersaturated magmas, what we find is that our saturated magma is able to cause an eruption before we start to relax the crust. Our magmas that start off with lots of water sometimes are able to cause an eruption, but they get very close to this time scale. And undersaturated magmas, the ones that don't have enough water, they sometimes take too long to cause that overpressure in order for it not to be relaxed by the crust. Okay, just bringing it together now. We wanted to understand how overpressure relates to eruptive style. And what we found is that when we started off with different water contents, so 4.5, 5, 6, or 7, this dictated what the peak overpressure would be. So for this particular magma at 200 megapascals, we're assuming that the peak overpressures are at middle water contents. Now, this is really interesting because it shows us that there's a sweet spot of high overpressures at saturated conditions. And when we superimpose the observations of the water contents that we can measure in explosive eruptions and in effusive eruptions, they look like this. So here you can see that explosive eruptions generally have middle type water contents, and effusive eruptions have either high water contents over here or low water contents. And this very well matches up with what we expect from our peak overpressures. So these are separate estimates and constraints, but they seem to match up with what we're saying in this particular talk. And coming back to the start of the talk, what it shows us is that the saturated water conditions promote higher overpressures, and we think that higher overpressures then initiate really fast magma ascent. And that means that we get less outgassing of volatiles. It leads to explosive eruptions. So we suggest that actually it's the volatile contents potentially that could be really important and driving these overpressures. And the overpressure is what drives the explosive eruptions. So I'll just do one or two more slides here very briefly. We did test the parameter space, not just looking at one depth, but looking at different depths, looking at blocky or like different shapes of magma reservoir and different kind of constraints over here. One of the interesting things we find, this is a complicated diagram. Again, we're showing time along the x-axis here. This is oversaturated, this is saturated, and this is undersaturated. What we find is that it's hard to trigger an eruption via cooling at a deep depth, okay? And that's because the volume expansion is suppressed by the lithostatic pressure. If you have shallow conditions, it's actually too compressible. There's too many volatiles in the system, and it becomes, it dampens a lot of the signature. So the highest overpressures we see are from magmas at these kind of mid-brown conditions at 6 kilometers. So this might control why we have magmas forming around that produce volcanic eruptions that are sourced from this depth. Potentially it's because they're at the right sort of conditions to produce a volcanic eruption. We also find that large magma underpressures may draw up magma from below. Okay. Now I'm going to skip over this briefly, but I want to talk about the implications for the future. And I can come back to under pressure in the questions potentially. So the implications of this study, this modeling study, obviously modeling studies sometimes have limited use for how we understand volcanoes or how to monitor volcanoes. But actually, I think this study can tell us something quite interesting about how we can best forecast explosive eruptions potentially. So we can detect the size and the shape and the depth of magmas via a seismic data, tomography, or even looking at depths of seismicity from our eruptions underneath volcanoes. So this can tell us about the overpressure and where we can start to model this. We find actually the problem with that is that sometimes there's little seismicity for internally driven overpressures. Okay, so what might be an interesting thing to do is to look at the deformation signatures. So this can be looked at with GPS, which can measure how the ground inflates, or even by satellites as well. So there was a study in Okmok, which is in Alaska in 2008, before the VEI4 eruption. And remember, this is a period where it had long periods of deformation, then a very short run-up of seismicity. So they measured the INSAR and GPS via this, and they were able to work out and calculate the overpressure from this. So in the years before the 2008 eruption, they saw that the volume was increasing, and they equated this to a pressure which they showed the pressure was increasing before the eruption. So perhaps it's something that we could do in the future is track overpressure in real time by looking at deformation. And of course, this has implications for eruptive style because this ended up being an explosive eruption as well. Another way of looking at it is something I've looked at briefly is looking at halogens. Chlorine, fluorine, bromine, things like that could be interesting. So just a quick summary here. I'm sorry I've talked on a bit. So this is just a summary to say that when recharge of magma, so magma's coming into the system, is low, but when crystallization is rapid, we see that second boiling could be an eruption trigger, could be a really good way of triggering explosive eruption, especially when it's faster than how the crust can accommodate it, even for conduction cooling scenarios. But what we find is that it's very hard for CO2-rich magmas to form eruptions in this process. So we think it's especially relevant for small reservoirs. But if we have pressure localization, then sometimes we think this can trigger larger eruptions. So the magnitude of the overpressure we think is affected by the initial fluid content and the depth. And we find this sweet spot at water saturated conditions. And this relates to eruptive style via this process of fast magma ascent. So fast initial overpressure drives that fast ascent, drives explosive eruptions. So this is potential for overpressure rate to be more important for triggering than a critical threshold as well. I didn't really go into that. But what we show is that seismicity might miss this volatile overpressure buildup, but actually deformation and gas monitoring might provide more insight. So thank you very much.
Thank you, Mr. Mike Cassidy, for sharing your insightful presentation, specifically about the magma overpressure, modeling, and also its implication for eruption triggering and style. And as we move forward, we will now be ready to take your question to the Q&A session. So for everyone who had question, feel free to raise your hand, or you can also use the raise hand feature or chat box on the Zoom for everyone who attends online.
Check. Do you hear me? Do you hear my sound, Mister?
Yes, thank you. Yeah.
Let me introduce myself. My name is Gede. I'm from my master students from Geological Engineering in ITB. So I was a little bit curious about the compressibility of the magma. So I want to ask how the procedure on measuring compressibility of the magma. And does the water content on measuring the compressibility of you? So if it was if it was been measuring, the value was only the pure magma compressibility or magma with water compressibility. Thanks. That's all from me.
Yeah, no, good question.
Okay, Mr.
So
directly.
let me see if I can go back to this. So actually, it's measuring all of the compressibility. So it's not just the magma, it's the magma with the volatiles. So if I go back to this one, show this slide here. So this is the initial, I'll get my little laser pointer. This is showing compressibility as we cool down in temperature. And at this stage, the magma has absolutely no volatiles that have been exsolved. So the volatiles are all in solution, but they're still accounted for. But then once you get to a certain temperature, when you have some crystallization, that triggers the magmas inside the magma to exsolve. So at that point, we do track the exsolution of the volatiles like water, CO2, and that's taken into consideration in this compressibility curve here. So as soon as those volatiles become bubbles, the compressibility goes up and up and up and up. And at this stage, when it gets to 900 degrees, etc., it just gets too high. It becomes too compressible. I hope that answers the question.
There are more questions to ask? That's all. Okay. Maybe another question from everyone here. Please.
Hello, Mike.
Yeah.
Thanks for your presentation. I'm Jananda again. Probably we've met before earlier of this year from online seminar. But
Oh, cool.
yeah, right now I'm a part of what's that? ITB petrology group. Now I'm joining. So I'm curious because I am studying similar thing, but from different approach. I was curious because you mentioned about a compressibility and overpressure from the experimental. Is there any effect actually from crystallization in multiple magma reservoir levels in the crystal cargo to produce different compressibility or overpressure trends? Because what I understand from your presentation, probably if we have crystal high enough crystal content, it will it will be easier for the vapor phase, let's say in this case water, to exhaust because of the surface tension produced by the crystal surface, right? And then probably will be trigger the outgassing, increase the outgassing rate. So probably can you elaborate about that? I'm still doesn't get
Yeah, sure. Yeah. So the rate of crystallization. So the crystallization, as you say, will trigger the release of volatiles to make them exsolve. So and that will occur because of a dilution, sort of a concentration effect. So if you take out crystals that don't have much water in, then the residual magma that's left over will have lots of water in. So it becomes saturated and becomes saturated enough to trigger trigger volatile exsolution. So it's not as much the surface tension that creates the crystallization. It's more how saturated the magma is in volatiles. The crystallization is really important though, because it's thought to, you're right in that if you have a magma that has crystals, it's more likely to form bubbles as well. So there is that relationship as well. So you're totally right. If you have too many crystals in the magma, then things can get locked up, so around 60%, the magma and everything just becomes too viscous to move and to erupt. So there is an upper end where it becomes too immobile. There's also been some studies about how crystals can actually enhance outgassing. So if you have lots of crystals, then they can form, or some crystals, then they can form permeable pathways more easily through the magma. So you're right that some crystal rich magmas can be more, they can allow more gases to outgas. It's just asking the question whether if you have a magma that's ascending so fast, then some of these processes aren't even important. So if you have a fast initial overpressure that happens to be fairly crystal rich, say like 20, 30, 40% crystal rich, then perhaps in a stable magma, that those bubbles within the magma will be allowed to outgas. But if you're driving such high overpressures and driving fast initial ascent, then it's going to be explosive anyway. and actually the rate at which bubbles can leave the system via outgassing will be a second it will be a second order thing. It's not as important as the initial ascent rate.
So, okay, thank you very much, Mike, for the explanation. How about if the case was the sudden decompression occurred, and then because we have, let's say, high ascent velocity, from the magma to the surface, and then it will, inhibit the, let's say, the crystallization and so on, and then promote the pressure accumulation at, near the surface. Can it be explained by this diagram for peak overpressure? Or
Yes, it's a really good question. So you're asking about decompression. Yeah. So it's a really good question. Let me see if I can go on to this next slide. So yeah, it's a really good question. So if you have some sort of decompression event, so for example, a Mount St. Helens event where you have a collapse of the edifice, or even an Anak Krakatoa event in 2018, where you had the edifice sliding into the sea, and then we had an explosive eruptions afterwards. So these are very much driven by a different process than what I'm talking about today. They're driven from the top downwards rather than the bottom, like an overpressure at the magma upwards. But I still think this has quite an important, what I'm describing here, I think is still important, because if you decompress a magma that's under a lot of pressure, then I think you can produce more explosive eruptions. So if it's already sitting at a magma reservoir, it's cooling down, but perhaps it's sort of saturated like this, then it might already have an excess overpressure. It might not be enough to trigger the eruption, but if you produce this trigger from above, like decompression, then it can cause the magma to kind of drive even faster ascent. Yeah, so you're right. So I think in those instances, the magma eruption's driven, it's not triggered by this overpressure, but actually the overpressure can actually help it to become more explosive potentially.
Okay, thank you for the insight, Mike. Thank you so much.
Yeah, good question. Thank you.
Okay, thank you, Sarjana, for the question. So we're gonna move a bit to the online. We'll check. There is already one question from Fahri Nabil Putra. So you can also check that on the chat box, sir. How fault line activities affect volcanic activity, or how much influence does fault movement has on volcanic activity? That's the question.
Yeah, okay, interesting. In the context of this talk, I think that it affects the crustal strength of the rocks around the magma reservoir. So if you have lots of cracks, fault lines around the magma reservoir, then it weakens the reservoir essentially. So let me just go to areas where I was talking about the critical overpressure. So over here, I showed a critical overpressure of 20 megapascals. If you have a very fractured crust, that's going to reduce that critical overpressure, and you might have a threshold to trigger an eruption might be about 10 megapascals, for example. And in terms of fault movement on volcanic activity, these can have so many different effects. It might affect the compressibility, the overpressure of the magma if the fault moved in a way that brought a magma reservoir together. So this might cause a squeezing of the magma reservoir, causing more overpressure, potentially causing an eruption. Yes. So in the context of those things, and of course, if we have a fault line that's near a particular magma reservoir, like what I showed here, then this is where the magma could utilize those sorts of pathways to get to the surface. And this is what volcanoes often do. They try to find the easiest way to the surface, and often it's around these kind of fault lines as well.
Okay. Thank you, Mr. Mai, for answering the question. Maybe for everyone who's in the Zoom and still have any question, you can use the raise hand feature or by using the chat box on Zoom. Okay, maybe for everyone who attends here in this room and still have any other questions? Okay.
Hi, I'm Meg. Thank you for a very insightful presentation. So I'm Astin. Actually, I'm an alumni from this Geological department, but now I'm currently working in Togo University, and my topic is more related to fluid rock interaction under high pressure temperature. So it's more about metamorphic process, and I'm working on the experimental side. So it's really interesting to know the effect of CO2 on compressibility of the magma. My question is really maybe a small question. I'm just curious, like how CO2 can control the fraction of water. Yeah, like what's the thing that control CO2 content and water content? Like, is that any particular depth that this ratio can change, or how is that? Yeah.
Yeah. So thanks, Astin. So your question was, what controls the water content or the CO2 content? Is that right?
Right.
Yeah. Yeah, it's a good question. So these can be controlled essentially by how the magma is formed at deeper depths. So deeper than, magma reservoirs, we assume are about 3 to 8 kilometers generally. But actually, there's lots of stuff that goes underneath this system, and this is, a lot of Mirzam's research as well. The stuff that happens near the slab, the volatiles that are driven off in the melting of the mantle that go through the crust. The crust itself might have bits of CO2. It might assimilate carbonates. We see this at Merapi. We see this at Popocatépetl, Etna, because we see xenoliths of kind of limestones and things like that. So CO2 can be from the mantle and driven by partial melting of the mantle as it rises up through the crust. And that means that some bits of slab or some bits of the mantle that form that melt just generally have more CO2 potentially. And this might be more CO2 rich in, for example, hotspot volcanoes like Hawaii or Tenerife and those areas like that. And then subduction zones like underneath Indonesia, generally the CO2 levels are lower, but they could be picked up by crustal rocks as well. And in terms of answering your question about how they vary with depth, then generally the CO2 will come out of solution and exsolve much deeper depths than water. So it's possible that there's CO2 in the magma, but if it's sitting around for a while, then it's possible that CO2 might leave the magma at deeper depth and just come up to the surface via diffuse degassing. And actually, we find this in volcanoes a lot. If you go to volcanoes, a lot of the CO2 that measured around volcanoes, not necessarily from the plume at the vent of the volcano, like sulfur or water or fluorine, chlorine, but actually the CO2 seems to come up through cracks and faults in the ground in a wide region around the volcanic edifice. So people measured this in Africa and other places where we find CO2 just comes from a deep depth and kind of rises up through faults around the magma and up through the crust and can be found quite in a diffuse area around the volcano.
for the explanation. So basically, CO2 can be related to a lot of factors like um, tectonic, uh, tectonic settings. Maybe that's really related.
Yeah, I think tectonic settings, CO2 varies, and the crustal composition as well.
Okay. Right. Thank you, Mike.
Thank you.
Thank you once again for answering the question. For anyone, again, in this room, please kindly, I would like to remind you all, if you have any question, please raise your hand. Or for everyone who's in the Zoom, who attends online, you can use the raise hand feature or the chat box. Another question, anyone? Okay.
Okay. Thanks, Mike. What incredible presentations. My name is Carson. I'm an undergraduate student in ITB. My questions is directly talking about the diagram that you showed before about the correlations between the overpressure and the cooling time of the magma itself. And
Oh, yeah.
I was thinking that is it um, is it possible for us to forecasting how the overpressure happen in the magma, and it would be so good if can be forecast the as you said before, if the oversaturated occurred, that would be proposed to the explosion itself, the volcano explosion itself. I mean, this is the summarization of my questions is this: is it available for us by this oversaturated model, overpressure model, to forecasting the volcano explosion itself? Thank you.
Yeah, this is a good question. I think so. With this timing model, I think it's difficult to forecast any volcanic eruptions, and the reason being is that this is a model that doesn't take into consideration all the kind of dynamic processes that would be happening at different volcanoes. So, for example, Kelut has an active geothermal system where we have obviously a lake at the surface, we have a lake, probably a reservoir beneath the surface, and there's likely lots of convection going on. There's faulting, as Abdullah mentioned, another question in the chat mentioned, faulting as well is going to increase the amount of cooling that you can get as well. So actually, just using this timing model is very tricky. And I should just say that it's not the oversaturated eruptions that produce the explosive eruptions. Generally, it's just the saturated eruptions that cause that sweet spot. So ones that have too much volatiles potentially are less good at forming explosive eruptions. But I think this is where more important is not tracking the timing of it, but also tracking the sorry, I'm just getting onto this slide here. Tracking the overpressure via monitoring. So this perhaps has more use, I think, in forecasting. So if you can model how, instead of just the timing of how long it takes for a magma to cool, because we don't know when the magma started cooling as well. That's quite hard to tell from forecasting. But if we were able to measure via GPS, via INSAR, the inflation of the system, like they've done in Alaska here, then we could actually work out that there is a lot of overpressure in this magma before the eruption. And this probably likely led to an explosive eruption before the 2008 eruption. So I think, and what we find a lot is that there's a little bits of seismicity right before this, maybe a few days before this as well. So if we know that there's lots of overpressure in the system by monitoring how the magma has inflated the crust, and if we see a large amount of a fast ramp up and high seismicity before, then I think this can tell us potentially is a good indication that they might have an explosive eruption.
So I hope it answered your question, and thank you, Mr. Mark, for answering the question. Okay. Maybe for anyone who still have questions, anyone? For the online attendees? Okay, maybe because there is no more question, I hope everything is already answered your questions. So ladies and gentlemen, that was the last question for our Q&A session. As we come to the end of presentation and discussion, we will now proceed to the handover of the certificate for our guest speaker, Mr. Mike Cassidy, who will be presented by Mas Idam. Okay. Before the operator can do. Okay. There you go. For Mas Idam, can you please present the certificate to Mr. Mike?
Okay. This is the certificate, Mike. Thank you very much. You always, give us the many new, idea or topic. Thank you very much, and belongs to, on behalf of the head of ITB Geological Engineering. Thank you very much. This is the certificate. Thank you, Mike.
Thank you very much.
Thank you, Mr. Mike and Mr. Idam. Okay, now let us take some photos together so our meeting today could be remembered for all the attendees. Who via Zoom, please kindly turn your cameras on. And for everyone who attends offline, maybe we can all come together to the stage. Thank you. Please. Okay. So ready? Oh, okay. Okay, is that ready? Okay, we will start the photo in 3, 2, 1. Another one. Okay, thank you. Okay, ladies and gentlemen, I would like to express our heartfelt gratitude for our speaker and all the attendees today. Thank you once again to Mr. Mike Cassidy for joining us and sharing your insightful and educational presentation.
You're
Okay,
welcome. It's
that's
great to
all
see you.
for today. My name is Tara, and I would like to take my your host for today. Wishing you a pleasant afternoon and see you at the future events. Terima kasih dan sampai jumpa.
Terima kasih. Thank you, everyone.
Thank you, Mr. Mike.
Thank you, Mike.
Thank you, Mas Mizam.
Yeah, thank you.
Terima kasih Pak Mirzam.
Yes, you might. I will send the presentation for discussion. Mas Hamzah Umar, terima kasih.
Terima kasih Pak. Izin live.
Yeah. Yeah, I will send the invitation. Yeah, to have discussion with you and Sep soon.
Yeah. Okay. Sounds good. Yeah.
Okay.
Great.
Okay.
All right.
See you. Yeah, see you.